I'm now pleased to introduce Tommasso Fraccia, who is with the Molecular Self-Assembly Lab at the ESPCI's Institute of Chemistry, Biology, and Innovation. I hope that I got that right, Tommasso. And he will speak to us about self-organization and catalysis in Coacervate-based protocells. So Tommasso, over to you.
Thank you very much for the invitation, and thank you very much for all the people that are still connected, especially in my time zone, in which the hour is very late. So I try to share the screen. So thank you very much. I'm a junior researcher at ESPCI in Paris, in France, and where I lead a small team that is called Molecular Self-Assembly Lab, in which we basically we study self-assembly and phase transitions in biomolecular solutions, and with the focus to use them to gain organization and catalytic activity in chemical systems. In particular, we use self-assembly to generate new assemblies starting from a molecular mixture that can be very complex, and we use phase transition as a tool to create phase separations and a way that can be used to select molecules, and if in those phases further phase transition can happen, we can have new symmetries, new function, and so on, and this can help the formation of organized and catalytic objects, and I will try to show that in my talk. And our interest lies in liquid crystal phases, in complex coacervation, and we are using microfluidics to prepare and to manage those things. So, as you all know, origin of life is a story of growing chemical complexity. So we know that if we look into space, we have a plethora of small organic molecules, and if we move out from this and in different environments, we can observe a growth of this chemical complexity. For example, in meteorites and comets, we have more complex molecules. But to find the most complex ones, we have to go to a planet. For example, on Earth, we know that we have RNA, we can have compartments, and so on. So it is like that life to emerge need a cradle. So a place with some conditions that we will know that can enhance the formation of life. And here I'm just pointing 3 points that for me are essential in for the emergence of life. Is the fact that if we are in a planet, we have liquid water, we have a stable atmosphere, we have cycles, and so on. What changed is the fact that we still have a certain complex system, complex distribution of small molecules, but in this case, their interactions are mediated with by the solvent, by the presence of solvent, and water is a wonderful solvent for the molecules, and with interaction with mineral surfaces and so on. Moreover, with cycles, we can have dry and wetting cycles that can enhance the concentration of molecules. And in these conditions, therefore, what can happen is that we can have self-assembly structures made of those molecules and even phase transitions. So basically, for obtaining biology from a chemical system, we have to face different problems, and I just highlight 3 of them. So we basically need some polymers, we need compartments, and hopefully we need Darwinian evolutions. So we need polymers because we need an object that is capable to store information, hopefully to display catalytic functions like ribozyme that we know, and best of our chance, those polymers can also self-replicate. Moreover, we need compartments because we need to gather and protect those polymers. We need to concentrate reactants, and the features that I would like to find in our compartments is that they could be capable of growth, divide, so to sustain replication. And those features, the presence of biopolymers and compartments, are necessary ingredients for a system that can undergo Darwinian evolution, in which our system we can provide variation in our systems, and we need that our system is capable to replicate, self-replicate with a certain degree of heredity in order to transmit the genetic information, and there should be some kind of selection based on some property of the system that will enhance the survival of some of those objects and instead esteemed the others. Today I want to show you how we can start to find those features in self-assembled Coacervate systems. Complex Coacervates are associative phase separation, which happen in solution of different polymers, which we have a certain attractive interaction. So, for example, the most known case is the case in which we have a polyanion and a polycation. Therefore, we have electrostatic interaction. The two polymers will make complexes, and they will undergo a phase separation between a dense phase that is composed by both the polymers and a very dilute phase. Of course, for this to happen, we need that the counterions of our polymers will be expelled from the dense phase in order to balance the osmotic pressure. And therefore, this phase transition is basically a transition that is entropically driven by the gain in entropy by the partitioning of the polymers in one phase and the counterions in the other phase. But and you can see on the right, this is the classical phase diagram of such a system, and which is the interesting thing. The interesting thing is that coacervation depends on the interaction, and the interaction between the polymers can be regulated by different parameters, such as temperature, pH, but also ionic strength, and so on. Therefore, if we prepare our system, what we see is that if we are in a certain condition, the system is uniphase. But if we prepare our system below this bell-shaped line, which is the binodal curve, then our system will phase separate into the two phases. And this is a tie line. That means that in each point of this line, 2, 3, and 4, we have the formation of this phase separation. And interestingly, in each of these points, the concentration of the polymers will be the same and will be exactly the concentration that we find in the intersection between the tie line and the binodal line. And this is a powerful system to enhance, increase the concentration of polymers that can be found at in a diluted concentration at the beginning, but they will be highly concentrated in the Coacervate phase. So in the last decade, Coacervate has been broadly studied and proposed as prebiotically relevant compartments, somehow as an alternative to membrane-bound compartments. I mean, in my opinion, there is no really a problem between saying, I mean, there is not a dichotomy between the membrane compartments and the membraneless one. They can have both played their role in the origin of life, and they can also have cooperate in some condition. But the reason by which the Coacervate has attracted the interest of the scientific community is the fact that they are very easy to assemble. If we have a polymer system, it's very easy that we will form a phase separation. And then the fact that Coacervates are formed also by prebiotically plausible low valence polyanions and polycations that can compartmentalize RNA and other molecules, and that's inside the Coacervates. It has been proved that it's possible to obtain ribosome catalysis and also templated polymerization. Moreover, the Coacervate themselves can exactly interact with vesicles and template the assembly of vesicles on their surface, but also they can form multi-phase droplets that can provide a way to increase the level of organization of those compartments, and then can also simple metabolism. And it's very nice to see that the investigation on Coacervate is finding so much attention now, while this idea of coacervation is a very old one, and Alexander Opper in 1924 already spoke about those Coacervates as possible primitive compartments. So in this talk, I want to show you some pieces of my research that wants to answer those questions. So can Coacervate can we increase somehow the level of organization of those compartments? And the second is, can we enhance non-enzymatic reaction inside those Coacervates? And the third one is, can we provide a stringent coupling between the content and the compartment? Especially this last thing is an essential feature for a protocell model, because will allow the coevolution of the compartment and the content. So the way we choose to increase the level of self-organization is to use double-stranded DNA. So when we started our investigation, double-stranded DNA was not very interesting for coacervation, because most coacervates were obtained with single-stranded DNA and cationic peptides, because they easily form liquid-liquid phase separate system, wonderful droplets, and so on. While with double-stranded DNA, the problem is that this molecule is more rigid, has a higher density of charges, and this often causes the formation of precipitates, because the complexation between the DNA and the peptide is very strong, and often leads to precipitation. Anyway, we were interested in this system, and therefore we performed a study of mixture of oligomeric double-stranded DNA, 12 base long, and the cationic peptide polylysin. And interestingly, we found that it's true. In many cases, we just found precipitates, but at increasing salt concentration, something different happened. Indeed, we have the formation of coacervates at very high liquid coacervates, isotropic liquid coacervates at very high salts, but at intermediate salt concentration, we found that we can get coacervates which has an inner organization. And those inner organization is typical of liquid crystals. Indeed, those droplets are birefringent. They show a texture, and I will show you later that they are inner organized. But moreover, we decided to treat thermally those kind of systems, and therefore we anneal the system. Then we cool them down, and we found that in many cases, even at lower soil concentrations, the precipitates were reorganized and formed other coacervates, which had different phases in their interior, different phases of typical of liquid crystals. So before going ahead, I just want to make a small parenthesis speaking about liquid crystal, because maybe it's not very familiar to all of you. So what are liquid crystals? We are familiar with them because we have them in our phones, in our tablets, and because in each pixel, basically, there are molecules that are elongated molecules. And those molecules can have as the peculiarity to show partially ordered states of the matter. And those partially ordered states of the matter are in between the fully disordered liquid and the fully ordered solid. And the spatial state of the matter is very useful for technological application, but is also used in nature. Indeed, we are full of examples of liquid crystalline phases that happen in biological system. For example, there is this beetle in which his color is the texture of his body are given by the fact that the ketene molecules can organize in cholesteric liquid crystals that gives them this particular color and which reflect light in a certain way, and that gave advantage to this kind of system. And moreover, there are many biomolecules that can order into liquid crystalline states, such as cholesterol, or there are also other active system like actin system that's from liquid crystals. So liquid crystal has to do with biology more than what we can think. But what I want to focus on is the formation of liquid crystal with DNA. And all those pictures are pictures of system made of DNA in a liquid crystalline phase. And you can recognize them because you can, if you observe them with polarized microscopy, you will obtain those wonderful birefringent textures. And the system, I want to stress this, are not pure crystals, but are liquid crystals. So they are fluid. They can flow. They have they have a certain fluid. And how liquid crystals are formed in a system of DNA oligomers. So if we have DNA that can pair and form double-stranded DNA, then we can have linear aggregation of those fragments. And once we have long enough linear aggregates, at high concentration, they can order into liquid crystalline phases. And we have different level of ordering. If we have just orientational ordering, we speak about nematic phase. If instead we are also positional ordering on an hexagonal lattice, we speak about a columnar phase. And in our coacervate, go back to our coacervate, we exactly find this. So in this case, it's not depending on concentration, but it's depending on salt concentration. We can have all the different liquid crystalline mesophases. So we can have an isotropic phase, then a cholesteric liquid crystal phase, then columnar, and then a columnar more crystalline one. And I mean, this those phase transitions are tuned by the salt concentration that allow us to explore the phase diagram. And basically, what happened in Coacervate is the fact that at different salt concentration, we have the separation of the system into two phases, and the dense phase as a concentration of DNA that allow the formation of those liquid crystalline phase. But what I want to stress again is the fact that, as shown by those FRAP measurements, the inner phase of those liquid crystal is still fluid. For example, this is the FRAP signal inside a cholesteric liquid crystal, and this is the one in isotropic liquid crystals. So the dynamics is slowed down, but the system is not arrested. It's still fluid. The interesting features of those liquid crystalline phase separation is that they balance. They have a balance between order and fluidity that can provide new functionality. And I mean, if you're interested in this, we just published a review that you can find on Colloidal and Science Interface, and that will review different. That is reviewing different systems made of biomolecules that provide liquid crystalline phase separation. But coming back to the interest for origin of life, which is the interest, is the fact that those kind of liquid crystal coacervates can strongly respond to variation in environmental parameters. For example, if we change temperature, so then we will have phase transition between the different phases that are driven by temperature. So at lower temperature, we can have a liquid crystal coacervate, but increasing the temperature, we have an isotropic phase, and then this is assembly of the system. And this thing is reversible. So by cooling the system, we will come back to the starting condition. On the other side, we can even dry or rehydrate the system. And as you can see in this video that has been speed up a lot, if we prepare a system in this condition in which we have almost crystalline coacervates, almost crystalline structure, then by drying, what happened, the salt concentration increase, and therefore the system makes transition between all the different phases, becoming liquid crystalline, then liquids, and then uniphase. And so, playing with temperature and the concentration, we can explore this phase diagram that is way, way richer than the phase diagram of simple coacervates, simple liquid coacervates. And this can provide the formation of phases that can have more or less functionality. The other thing is the fact that liquid crystal coacervate strongly depends on the properties of the constituent molecules. So, for example, we investigated the dependence on DNA length, and we found this behavior. So, as we increase the DNA length, then the stability of the coacervate increases. You can see this by the fact that the critical salt concentration increases, but also the persistence of the different phases is observed at higher salt concentration. The other point is that the system strongly depends also on DNA sequence and in particular on their structure. For example, we studied different systems in which we are keeping a fixed core of the DNA sequence, but adding different different sticky ends. With this is a way in which we can tune the interaction between the different DNA fragments. And what we saw is that the stability of the coacervate follow the strength of the interaction between the different DNA. Therefore, for example, a strand that is interacting with GC pairs lasts for at higher cell concentration, while if we have AT, it will last only at low cell concentrations. Before we exploit this to make combination of different DNA molecules with different length and different structures, and we found several combinations in which we can have the formation of multi-phase coacervates, which means coacervate which have inner phase separation between a liquid crystal phase and an isotropic phase. And as you can see in these cases, we tagged with red fluorophore the one sequence, and a yellow fluorophore another one, and we have separation of the different sequences in the two phases. But on top of this, this kind of phase separation is also capable to partition different gas molecules that can, of course, depending on their properties. For example, if we have a single-stranded DNA, they will or double-stranded DNA, they will partition in the liquid phase of the multi-phase coacervate, while if we have very small molecules, they tend to they don't partition. And so we can exploit this difference of partitioning of gas molecules to trigger reaction inside liquid crystal coacervates. And also there is a temperature dependence. Therefore, we can melt one of the two phases at increasing the temperature, and when we decrease the temperature, the phase will be formed again. And therefore, in this section, I show you that the use of double-stranded DNA allows the formation of liquid crystal coacervates that can be very useful to increase the level of organization inside membraneless compartments. And therefore, here we can provide different phases, and we can partition gas biomolecules, and we can use them to trigger reactions. So in the second part of the talk, I want to show you how we can use coacervate to enhance non-enzymatic reactions. So the basic point is the fact that in the liquid crystal phase, the terminals of the different oligomers are kept in continuous physical contact. And we ask ourselves if this proximity can favor the formation of phosphodiester bonds. We already investigate this system in segregative phase separations, and this was working. But in the last years, we investigate that in coacervates. So we perform coacervates with this mixture of DNA and trans-isotope, in which, depending on cell concentration, we can have different phases, and we add EDC to activate the phosphates and to drive the reaction. Interesting, in this system, we saw that, okay, if we study a system in which we don't have coacervate, the reactivity, the yield of the reaction is very low. And this is the yield after 24 hours. But in coacervate, instead, we can start to see longer products and a broader product distribution. But if we go also to liquid crystal coacervates, we can see that this reaction is strongly enhanced more than in the isotropic phase, and this causes a shift of the product distribution towards longer strand. And so, in this case, the ligation efficiency is enhanced in the coacervate, but also depends on the coacervate phase.
Tommaso, pardon me,
Yeah.
We're running out of time. If I could ask you to try to wrap it up.
Yeah, sorry.
Thank you.
Okay, so I skip this, and just one minute and I will finish. So, an interesting thing is the fact that we found the effect of the ligation reaction on the coacervate themselves. So if we start with coacervate in a certain phase at the beginning, after 24 hours after the reaction is performed, we have a phase transition. For example, isotropic coacervates start to show the nucleation of liquid crystal coacervates at their interior, and therefore the formation of a multi-phase coacervate. Therefore, the reaction is inducing a morphological change to the compartment, and therefore in this system we can have a coupling between the content and the compartment. So to summarize everything, we can produce different coacervate phase by choosing different DNA molecules that are differ in sequence, in length, and or interaction. Then we can perform ligation reaction that are dependent on the phase in which they are performed, and the coacervate phase will respond to the new DNA population. And therefore, in this way, we can have a connection between the compartment's morphology, the compartment content, and the reaction that is happening inside. And this system can sustain a positive feedback loop in which the elongation will enhance the stability of the coacervate, in turn favoring the elongation. So with this, I conclude, and I want to thank all the collaboration, the collaborator, and the people of my group, and thank you all for the attention.
Okay, thank you very much. So that concludes the scheduled presentations for this second Life in the Universe conference. Before I turn it over to some of my colleagues on the organizing committee, I would just like to say that as a representative of PAST, we were delighted to have collaborated once again with Breakthrough and the South African observatories to put this conference together. We think there's a tremendously fertile ground in this collaboration to develop some meaningful science, and also to develop public interest, for example, through PAST's All From One campaign that Bernie mentioned on day one, and other outreach activities we can come up with. And we look forward to the next conference and to the potential for developing this multidisciplinary effort. I'd now like to turn it over to Barbara Sherwood-Lohler and Pierre Durand for a few final remarks, and perhaps our co-chair, David DeBoer, will also have a last word. Barbara?
Thank you. Yes, we'll try to keep it pretty short, I think, at the end of what's been an extraordinary 3 days, but a long and very diverse and therefore thought-provoking. Thank you to all the speakers, the audience, the organizers, especially to Dave and Andrew and Bernie. and all the team of co-organizers who pulled this together. As you can see, there was an attempt to really try to reflect the full diversity across all kinds of spectrums in terms of thinking about the search for life. And we've seen that reflected in the themes, moving from the inner solar system to the outer solar system to exoplanets, but in particular, not just a target-driven broadening, but also, I think, a really conceptual broadening of how we go about this, from the talks from Breakthrough Listen and Breakthrough Starshot to the new thinking about even the rocky planets, Mars and Venus. These are ones that we've been, have got an enormous amount of history and investigation going on. But even there, we're seeing new conceptual advances with a focus on the potential for subsurface life, subsurface processes, for instance, related to methane, with a focus on preservation of organics and on atmospheres. And then in particular as well, a really interesting set of discussions around sort of community work together, thinking about things like baselines, universal biosignatures, abiotic signatures, technosignatures, criteria for life detection. All of it, I think, kicks back quite nicely to the themes that Lisa opened us with, where she talked about habitability being a concept that's really a dynamic concept, because habitability, of course, is changing in space and time, and therefore the signatures must be thought about in the context of those changes in space and time. So I think these were some really fruitful areas that I know will be with us, not only if we do this workshop next year, but as we move forward in this really exciting and rich discipline. And I'll just turn it over to Pierre then.
So I really just want to keep it really short and just want to endorse everything that Barbara said. And thank you very much to the participants and all the speakers, of course. I've received so many emails from other people around Africa. Just want to let you know, they're just so happy to have been able to listen to all these experts from so many different fields speaking about it. So besides the speakers and the participants, I really want to extend a great thanks to my colleagues from this organizing committee, Barbara, Jill, Bernie, Robert, and everyone. And of course, a very, very special thank you from all of us to David, who was the main driving, the person who did the nuts and bolts stuff. So David, really, we're all very grateful to you, and we really hope this happens again next year.
All right, well, sorry, just to have to unmute myself. Finally, thanks for letting me give the final closeout very briefly. On behalf of the full SOC, who was obviously very involved in setting the program and finding the speakers, I want to thank all of the speakers for a fascinating and stimulating 3 days of talks and discussion. I do think that one would be hard-pressed to find a more broadly cross-disciplinary set of talks, which really is exactly the drive and vision that Bernie Fanneroff had for this workshop, and he's really the spiritual guide for this endeavor. As we know, it's valuable and important to look across all the different fields that are investigating our origin story, which from the Big Bang to Luca to our first human ancestors, as well as to our current technological selves that are exploring the universe and trying to find and tell that story. We also need to make sure to think and dream for the future. And so hence the title of this workshop. We hope that some linkages have been made these few days among the participants, and that will prove interesting and fruitful over time and hopefully present at future conferences like this. Thanks to the sponsors, the Breakthrough Initiatives, the Paleontological Scientific Trust, South African Radio Astronomy Observatory, and the South African Astronomical Observatory. As mentioned earlier, the talks will be made available, and I'll send around a link when we get those out on the web. And of course, as mentioned, you can, I'm sure, Google Life in the Universe on YouTube. Thanks again to all those who attended across the very many time zones and for sacrificing evenings and mornings. And to export tomorrow's American holiday, happy Thanksgiving to everyone, and take care.